Hey everyone. Today we're diving into a classic programming puzzle. It's one of those problems that looks pretty simple at first, but the solution is just wonderfully clever. The challenge is this: how do you find the exact middle of a chain of data if you have no idea how long it is? And that's really the heart of it, isn't it? It's a riddle. Imagine you're walking down a long, winding path. You can't see the end. How on earth would you know the exact moment you've hit the halfway point without first walking all the way to the end to measure it? That's the puzzle we're going to solve. So this chain of data has a name in programming. It's called a linked list. And the best way to think about it is like a conga line, right? Each person in the line only knows who's directly in front of them. You can't just peek ahead and see how many people are in the line. To figure that out, you have to start at the front and tap every single person on the shoulder one by one. Now, here's the catch that turns this from a simple task into a really interesting puzzle. We have to be efficient. The real goal here is to find that middle person in the Congo line by walking past as few people as possible. We are looking for the solution with the absolute minimum number of steps or iterations. Okay, so when you first hear this problem, what's the first solution that comes to mind? Well, there's the obvious, straightforward way. We'll call it the brute force method. And, it works, but it's not what you'd call elegant. The logic is super simple. First, you walk the entire conga line just to count everybody. Okay, you count 10 people. Great. Now you know the middle is the fifth person. So what do? You walk all the way back to the start, and then you walk the line again, this time stopping when you get to person number 5. See? It works. But you've had to walk the line twice. And that brings us to the final verdict on this method. Does it work? Yes, absolutely. You will find the middle link every single time. But is it efficient? Oh, not at all. It totally fails our main challenge of using the minimum number of steps. We can do better. Trust me, we can do so much better. And that leads us to the really cool solution. It's a beautiful algorithm, and it has this great nickname, the tortoise and the hare. This approach is all about changing the way you think about the problem. The big idea behind it is actually pretty simple. Instead of having one person walk the line, we're going to use two. In programming, we call these pointers, but you can just think of them as 2 fingers tracing along the list. And here's the trick. One of them is going to move slowly, and the other one is going to move twice as fast. Let's walk through this. Picture it. We take our 2 racers, the slow tortoise and the fast hare, and we place them both right at the starting line, the very first link in our chain. And they're off. For the first step, the hare leaps forward 2 spots. At the same time, our slow and steady tortoise just takes 1 single step forward. Right away, the hare is starting to pull ahead. And this pattern just keeps going. The hare jumps another 2 links, and the tortoise clods along, moving just 1 more link forward. The distance between them keeps growing. But don't worry, there's a method to this madness. So the hare is just racing along, always moving twice as fast as the tortoise. Because it's so much faster, it's obviously going to be the first one to hit the finish line, the very end of our list. And when that happens, well, something amazing is about to be revealed. And there's the magic. The exact moment the fast hare reaches the end of the line, you look back and the slow tortoise is sitting perfectly on the middle link. It's genius, right? By the time the hare traveled the full distance, the tortoise has traveled exactly half the distance. No counting, no going back to the start, just one elegant race. So this whole tortoise and hare story is a great way to visualize it. But how do we actually tell a computer to do this? Let's take a quick look at the C program logic that makes this race happen. This little bit of code, this while loop, is the entire engine of the algorithm. It basically says, keep this race going as long as the hare pointer isn't at the very end, and as long as the spot in front of the hare isn't the end. That second check, the hare.next part, is super important. It stops the hare from trying to jump 2 spots when it's only 1 spot away from the finish, which is what keeps it from crashing. Okay, so now let's put our 2 methods, brute force versus tortoise and hare, into the ring for a final showdown. When it comes to the race for efficiency, is there really a clear winner? Oh yeah, it's not even a contest. Just look at the data. If our list has n links, the brute force method, with its 2 passes, takes about 1.5 times n steps. But the tortoise and hare method, it only takes half of n steps. That means it's about 3 times more efficient, and it does it all in one go. And that right there is the mic drop. 1 single pass. We solved the riddle, we found the middle, and we never, ever had to go back to the beginning. That's the very definition of an elegant and efficient algorithm. So, what's the big takeaway here? It's that the obvious brute force solution is almost never the best one. By just thinking about the problem a little differently, by using two pointers moving at different speeds, we turned a clunky two-step process into a clean, beautiful, single-pass solution. And that really gets you thinking, doesn't it? We unlocked this whole puzzle with one simple, clever idea. It makes you wonder, what other problems out there that seem way too complex, or maybe even impossible, are just waiting for the right clever algorithm to come along and show us a beautifully simple solution?